So in this chapter, I'm gonna try making it short, as if it exceeds like 25 minutes. Again, I'm sorry. And again, I'm sorry if I start speaking in Arabic suddenly, because I don't think I could hold a full sentence just speaking in English properly, I think. I just did that. So this chapter basically is about microscopes, and there are two parts of this chapter. The first part talks about the theoretical or the mathematical part of how microscopes work, and then the second part talks mainly about the types of microscope. I'm not gonna go over the types because I'm pretty sure you guys have been bored of this throughout your undergrad life. So I'm gonna explain the first part. So the basic concept of microscopy is that our naked eye. So let's assume this is my eyes. Very beautiful eyes. Okay, my eyes can only see anything down to 0.25 millimeters. And what this means is basically that when I have two dots, the ability that I could differentiate that, you know what, these are two distinguished dots, comes down only to 0.25 millimeters. Again, what does this mean? The most I could actually differentiate down to, or say, you know what, these two things are actually separate, or two different parts or objects than one another, is down to 0.25 millimeters. Anything below 0.25 millimeters, I am unable to distinguish that, you know what, these are actually two dots or 2 points. For example, if I draw you, like you guys, I'll just draw like two dots over here. These are two dots, they're clear, yani, kind of. If I zoom out, I really can't like differentiate that, you know, it's two dots. Because my resolving power, or my ability to actually see, becomes limited due to my resolving power, or I'm gonna explain what resolving power is in a bit. So basically, the concept of microscopes came about that we can't really see small things, we're blind, and we need something to magnify or make this bigger. And why do we need that? Because we have stuff that we want to study about, like bacteria, viruses, parasites, fungi, and they all come in the nanometer and micrometer range. So it's really something we can't see with our naked eyes. So after that, scientists created the microscope. But when they created the light microscope, for example, they had a lot of problems. The main two problems is that you have an exceedingly small dimension. I can't even breathe. And what this basically means is that, okay, maybe I do have a cell and I do take it under, for example, a microscope. For example, let's imagine this is like a microscope with its stand or whatever. And you place the cell, you mount it, blah, blah, blah. And what you see under the microscope is, in fact, you do see the cell. But the problem is, what if I want to understand, or I want to study the nucleus, or I want to study the ER, for example? So here comes the problem, is that we want to understand, or we want to see really small dimensions that can't really be seen using normal microscopies. And it comes with hand that the problem is, yes, I could see these bigger dimensions, but these like small dimensions over here, they're actually exceeding what the microscope can actually see. So this is one of the main problems that scientists or researchers had. Another problem is that our cell is not that transparent. It's not that colorful as the textbooks, for example, or in the slides or whatever. Like normally, it's actually transparent, and we do have a lot of issues by. You can't just take a cell sample and just stick it in the microscope, and you're like, yeah, this is a cell. I can see the nucleus. I can see the ER. I can differentiate between the ER and the Golgi. You can't do that actually. So the second problem was the cell is too transparent, and when you start, for example, projecting light on it, it just scatters everywhere because it's just literally transparent. So these are the two main problems that they actually faced. So how did they fix these problems? So for the first part, when they were like, okay, you know what, we have a problem with our dimensions. We want to see, like, wait one sec. We want to actually see what's inside the cell, and that's like one of the main issues. So what they did, or what they explain it, how they resolved this issue, is by fixing something called the resolving power. And what the resolving power is, basically, when I was talking up here and I'm like, the ability to differentiate between 2 points and distinguishing that, you know what, this is point A, this is point 2B, and these are different points that I can, with my naked eye, differentiate. But like for example, this small dot that I used to think it's like a whole dot, actually, you know what? I need a higher resolving power in order to be able to differentiate that, you know what, this is point A and this is point B. So the higher the resolving power, the more I could see to actually differentiate between point A and point B. So this is the main concept with just figuring out how do I differentiate between, or how am I able to actually start now going into smaller dimensions, for example, maybe from the cell to the nucleus, and maybe from the nucleus to the DNA or whatever. Sorry, I don't know, I'm breathing a lot. The second point is that they said that our cells are transparent. And I think this was very related, by the way, to the next chapter. And the way they overcame this problem is by three ways, all right? They either stain the cell, and when you stain the cell, you actually have a chemical that's present on the antibody, on the antigen, blah blah blah. You end up doing IHC, all right? So there's like chemical staining. I'll just write chemical staining, all right? The second thing you could do is you could add the fluorescence that could basically bind. It's an antigen that has a fluorescence that emits light, and how you're gonna actually view that is that you're gonna use immunofluorescence microscopy. This you could just use it under the normal light microscope. The third one is another type of microscopy again, which is the phase contrast microscopy. Okay, I'm not gonna go over this one or this one because like they're just types of microscopy and they're like in the slides later on. So the whole goal of this chapter, or the whole goal of using a microscope, is that we really just want to make things bigger. We want to see things that can't be seen with our normal naked eyes, and we want to be able to differentiate between point A and point B, as I showed you guys in the example above. So like again, this is point A, this is point B. They're different, A, B. But when I zoom out, I really can't differentiate. So my goal is to actually get a microscope that could help me distinguish between these 2 points. So the principle of microscopes, as I said, we were just through structures may be resolved, which cannot be resolved with you can't just see it with your naked eye. So what are the things that microscope actually requires? The first thing is the magnification. And it's not only the magnification, it's also the resolving power. And I'll explain a bit. So the magnification has, here it's written a ratio. Anytime you guys hear a ratio, just know it's going to be like something of a fraction. Okay, so there's going to be a denominator, a numerator, and it's going to be some sort of ratio between them. So magnification depends on two things. What we actually see with our naked eye, and what I will actually look at under the microscope. So let's assume this is the microscope. I'm looking at it with through the ocular lenses, or through the lenses. And what I see is actually just like, I don't know what it is. It's just like these 2 points. You know, it's like I can differentiate, you know, this is point A, this is point B. So magnification, oh, this is too tiny. Okay, so magnification, okay, well, I don't know how I reached the masters with really bad spelling. Magnification, okay, basically is a ratio between two things. What we see normally and what has been seen under the microscope. So it's the size of image under microscope. Again, I don't know why I'm breathing heavily, I'm so sorry. Under the microscope. And what is the natural or the actual size of the object, or of these 2 dots, assumingly right now. So this is what magnification is. But when you use the microscope, you do realize that we do have several lenses. It's not just like one lens that we keep changing, which is the objective lens. And I know you guys have seen like this is the microscope, for example, and it has like several lenses over here and over here and one over here. And these are actually our objective lenses. And I think there are 4. We have 4x, we have 10x, we have 40x, and we have 100x. So this is what we call the objective lens. The other lens that we use is the eyepiece, or the ocular magnification of the ocular, or the eyepiece. Okay, this is usually fixed in our microscopes, normal microscopes, but in advanced microscopes, I think they could change it. I'm not sure about this again. Maybe this is out of my pocket. No, it's normally 10x. So we have to consider that there is another magnification called the total magnification. Okay, guys, I'm not just writing these equations from my pocket. He literally said it over here, but he could have just wrote it as an example. I don't know why. So the total magnification is basically multiplying the magnification of the objective by the magnification of the eyepiece. And this gives us the total magnification. So let's assume I'm using the least number, so like 4x objective. 4 times 10 gives me a 40x total magnification of the specimen under the microscope. Sorry. Anyways, so this is the first part, that's the magnification. But magnification is not enough in order to get like the soothing picture that you want to get in the end. Because for example, take your phone and for example open the camera app and like just keep getting your phone closer and closer and closer to the table, for example, or to the wall. Or try zooming in closer and closer and closer to anything. Alright? Yes, you will magnify it, but another problem is it's not going to be as soothing, as soft, as defined, as clear, or as, for example, over here, the resolution is going to be really low. So another thing that you have to consider is the resolving power. Again, as I said, resolving power. And again, what's resolving power? It's basically the ability to differentiate between 2 points as separate. I could say that, you know what, point A is literally point A and point B is literally point B. It's not A and B are one. So the resolving power is as important as the magnification. But he placed this picture over here. And he was talking about wavelength, and because I don't remember anything from physics class, I'm just going to give you a mini crash course about what a wavelength is. So when a wave happens, for example, let's just go like this, right? So these are 2 waves happening. We see that we have over here 2 peaks, peak number 1, peak number 2. The difference between peak 1 and peak 2 is called a wavelength, all right? And how this comes hand in hand with the resolving power is that if we have a really high wavelength, or the distance, or the number between peak 1 and peak 2 is the wavelength. So if the distance is really, okay, let's write it somewhere else. Let's write it something else. Cut. Okay. So if the distance is really long, okay, English kind of whatever. No. The distance is long, okay, you have a higher wavelength. If the distance is short between the 2 peaks, you end up having a shorter wavelength. So what does a shorter wavelength or a higher or a longer wavelength actually mean? As you can see over here, that he's saying that as you move like this, the resolving power actually increases, which basically means when we have wavelengths that are really far from one another, you have a really low resolving power. So the distance is long, the wavelength is really big, which means you really have a low resolving power. But when the wavelength actually, or the length of the wavelength actually shortens, you tend to have longer resolving power. And again, do we need the resolving power that's high? Yes, of course. The higher the resolving power means the deeper I could go inside to be able to differentiate between 2 points. That's it. That's literally it. So this is why he had this picture over here, and I'm pretty sure this is gonna be like an MCQ question. So the second thing he was talking about, or he placed just some definitions, is basically, okay, now we understand that a microscope needs to have good magnification and has a really good resolving power. But then how do we say that, you know what, this microscope is actually good? And it depends on 3 things. Or when I say a microscope, okay, and I want to associate it with it being a really good microscope, I need 2 things actually. I need it to give me a clear picture, and I need it to give me, oh, one sec. I need it to give me a detailed image. So based on these two things, I could say, you know what, this microscope is actually good. And how do you achieve this? You will achieve it through three things. The first thing is the NA, or the numerical aperture. I don't know if I'm saying it right or wrong. Number two is the resolution power. Number three is the definition, or how defined the picture looks like. Definition, sorry. So the first thing is the numerical aperture. And I'll just explain it as like, I kept reading this line again and again and again, and I lost my mind. Basically, the dummy explanation of what a numerical aperture is basically how good the lens is at catching all the light that has been scattered and showing the fine detail. But there's an equation for the numerical aperture. You can see it over here. So it's basically NA, so the numerical aperture, equals to N sine. I don't know why it's U. Isn't it supposed to be alpha? I'll just write alpha. NA equals to N sine alpha. We have two parts of this equation. We have two parts of this equation. We have the N and we have the sine alpha. What the N is basically, it's the refractive index. And what I mean by refractive index is that how much does this medium tend to bend the light or whatever is passing through, okay? So for example, in air, we have a refractive index of 1. Let's go to something more denser or a thicker medium. For example, like oil. We use it in microscopes. I'm not sure. It has like a 1.515. This is what I wrote in the notes, but I'm saying somewhere here that it's 1.4. And the thicker the medium, the higher refractive index. And as you can see, this equation is fully just multiplication. So if we increase n, we end up increasing the numerical aperture. This is one thing. The second part is the sine alpha. Let's keep the sine on its own. Let's go to the alpha. What alpha basically means is that when, for example, this point is projecting the light, okay? It's the angle or half the angle of the cone of light entering the lens, okay? So let's assume that this is the lens over here. So what the alpha is basically, as I said, it's going to be half. So let's put like a line to differentiate, so half. This angle over here is actually the alpha, all right? So this is the number you're going to place over here, okay? Again, it all comes with like simple calculation, their multiplication. So as this part increases, the NA increases. I think you guys know this simple math. The second thing that we talked about over here is the resolution. And when I say resolution, again, I just said it like 300 times. The resolving power, or the resolution, is the ability to differentiate between 2 points as separate or distinguished points. But I kept saying resolution, and I never explained anything besides the wavelength. Actually, it doesn't only depend on the wavelength, it depends on something else. It also depends on the numerical aperture, okay? So, when I say resolving power or resolution, okay, it basically depends on the wavelength and it depends on the NA, numerical aperture or whatever. So let's look at the equation he actually placed here, or what, I don't know how to say his name, so I'll just refer to A's law. So this equation has two parts. It says D equals to wavelength over 2 n sine theta. And I'm pretty sure we just saw this part over here. This is the NA. So we could basically replace that. This equation is basically D equals to the wavelength over 2 times NA. This is what we could write it into based on understanding. Okay? But I'm just talking about resolution. Where is resolution considered over here? It's not directly considered. So the D is basically the minimum resolving distance. So when I say, for example, I have a microscope that can give me, for example, a 0.25, I don't know, micrometer resolution. Okay? And I have another microscope that gives me, for example, a 0.1 112 nanometer resolution. What do these numbers mean? Basically, I could go down up until the smallest number being 0.25 micrometers. This is my maximum ability in order to distinguish between 2 points. But this microscope over here can go even further down to 0.112 nanometers. So the D basically talks about the minimum resolving distance that I could give you guys. This is the minimum I could actually like. Okay, so what this basically means is that the minimum that I could reach to is 0.25 micrometers, for example. Anything below that, I could not. So the minimum number is from 0.25 up until whatever number you want. For example, I don't know, whatever number you want, but أهم شيء, it's above 0.25. So he has this equation, and this equation has two parts. It has the wavelength and it has the 2 times NA. I'll just do a simple calculation that I already did and I just erased where we're gonna fix the numerator to a constant, and then we're gonna fix the denominator into a constant and see what happens. I'll just explain what I'm gonna do right now. Okay, so let's make like two tables. All right, the first one is like the wavelength. The second part is the 2 times NA, and the third part is the D, where you're gonna do wavelength over 2 times NA. So in the first part, we're just gonna keep changing the wavelength. So I'm gonna give you a wavelength of, for example, 200 nanometers, and then we're gonna basically increase it to, I don't know, 700. We're gonna keep the NA fixed as 1, so it's gonna be 2, 2. The numbers that we're gonna get is 200 divided by 2, which is 100, 700 divided by 2, which is 350. And what I said just now is that the smaller the number of the D, okay, the deeper I could go in, or the more smaller dimensions I could go in to give you a picture. So this is better. The 100 is way better than the 350. And I just said upstairs. I just said in the slides above that when we looked at the wavelengths, when the wavelengths had really big or longer wavelengths, okay, it gave me a really lower resolution power, which makes sense over here. Because look, when we increased the wavelength from 200 to 700, we ended up having a lower resolution power of a D that's 350. Basically, I could only go down to 350 nanometers, for example. But the first one could go down or deeper into 100 nanometer scale. So if this is the first one, which has a really high wavelength, the second one is basically, for example, gonna have like shorter wavelengths. And I said like in the slides above, shorter wavelength is better because it gives me a higher resolution power. Just explain it here. Shorter wavelengths, higher resolving power or resolution power. So this is when you fixate or you increase the wavelength. So let's do the other table where I'm gonna keep the wavelength as the same, so 100, and the second one is gonna be 100 again, sorry. And I need to check something. 200 over 2 is 100. Okay, yeah, makes sense. And the second one is 2 times the numerical aperture. And I said I'm gonna basically over here change the NA. So let's keep the first one as 1, the second one as 2. By the way, these are just numbers from my pocket so you guys understand the concept. So it's 2 times 1, 2 times 2, and remember it's gonna be the wavelength over the 2 times NA, which gives us the D, which is proportional to the resolution power. So 100 divided by 2 is 50, and 100 divided by 4 is 25. Which one is better? The one that's better is definitely the 25. Why? I'll just write like nanometers, I'm just assuming. It basically says that I could go down the minimum number or the minimum distance that I could give you in order to differentiate between 2 points is down up until 25 nanometer, which is way better than saying, you know what, I could differentiate between 2 points that are 50 nanometers apart. The smaller the number, the better the resolution, which comes again hand in hand with the equation of NA. NA basically says that the N, which is the refractive index, times the sine alpha. If you end up increasing the NA, if you increase the NA, you basically end up increasing the resolving power, which gives you the ability to distinguish between 2 different points. So what this equation basically says is that the D, or the minimum distance I could achieve based on 2 factors, or technically 3. The wavelength the refractive index, and the angle or the scattering amount that I'm gonna give for the light to be spread, or how wide the light is actually. I don't know how I'm speaking literally like I'm drunk. I don't know. So basically this equation, I need to fix the my notes because I wrote it's directly proportional. It's actually inversely proportional, because as I said, if we have a really high D, okay, it basically means we end up having a really low resolving power or really low resolution, okay. But as the D actually decreases, the smaller the D, okay, it basically says over here, the smaller the D is, like, it gives you another minimum to reach to in order to give you a better resolution of the specimen that you want to work with. So the things he's talking about over here is basically, let me just see. Oh, and the third thing over here as well is the definition. And the definition is basically how defined it is. Maybe you see something under the microscope, it might have blurry lines, like you could see a cell like this, or you could see a cell like this. So the more unblurry it is, the more defined it is. Okay. So another thing that this is basically, he's just talking about like simple calculations into this equation. I said the things that cause is or influence this equation is the wavelength, the refractive index, and the angle that the light is, how wide the light is actually. And this is the same equation again. I don't know why he keeps writing it like 300 times. So it's the wavelength over 2 times NA, numerical aperture of the objective lens. And what he's also talking about over here is the working distance. I think you guys know what the working distance is. Basically the distance between the slide or the specimen and your objective lens. Which actually turns into a problem, as the slide mentioned, that there are limitations to this. So over here, we're going to be talking about, there are a lot of issues that actually come with trying to image, for example, a specimen because of the lens. And like these problems will often lead to having like a blurred or distorted image or a fuzzy image, or like you're not going to end up having like a sharp or clear image. So there are a lot of issues, but the main two most common issues are spherical and chromatic. I'm not going to attempt reading this word, so I'm just going to say A. So chromatic A and spherical A. The first issue is spherical A, which basically means that, for example, this is what I usually want out of my lens. For example, I want it to refract all the light in order to be collected at one focal point and be like, you know what, if it's met at this one focal point, it's going to give me a clear and sharp image. But the problem is with this piece. If this piece is not curved correctly, it ends up having a problem where the light is not actually refracted into the focal point, it's actually refracted way before the focal point. The light that's way closer to the edge starts meeting up way sooner than the focal point that it's supposed to meet at. So for example, this is going to meet somewhere here. So this is going to be bent over here. These points are going to be bent over here. And so on and so on. And you're just going to end up having a really fuzzy picture because of this problem, which is due to the eyepiece or this lens over here. So as you can see, they're all supposed to meet here, but they're not. And because they're not, you end up seeing something very blurry or fuzzy under the microscope. This is the first problem. The second problem is that light is indeed white, but when we see white, it's all the other colors but white. So what it basically means, or what it basically causes, is that when white light passes through, for example, the lens, it acts like, it acts like a prism, where I get into white and it starts emitting all the other colors but white, which is basically dispersion. And what this causes, again, is the same issue we were facing with spherical aberration. I don't know how to say that. Where you're gonna have a lot of colors, and each color definitely focuses on a different point, and then you're gonna have a problem with the structure, and it's not gonna be focused. It's gonna be blurry. It's gonna be misaligned. It's gonna be fuzzy, and it's gonna be funny to look at under the microscope. So these are the two main problems that they face while using the lenses of the microscope. And I talked about magnification. Um, uh, I'll explain the 250 millimeters. I just explained before in the slides above that the total magnifications depend on M1 times M2. What's M1? M1 is the magnification of the ocular. Okay, where did it go? Okay, M1 is basically the objective lens times the M2, which is the ocular or the eyepiece. This is basically M1, M2, and we know that M is, for example, the total or overall magnification. But then we see something called the D over 250. Now, I didn't include it in this equation because typically it's times 1. The 1 is a result of D over 250. So if it's 1, the D is probably 250. Where does this 250 come from? So when you look at, for example, the objective lens, there is, I don't know how to explain this, but the distance from the objective lens to the image is 250, and there's a basic calculation that you just put the distance. The distance is basically, again, from the objective lens to the image, which is 250, and the other 250 is actually the length of the microscope itself. So 250 over 250 is 1. So it typically cancels out. We don't even include it. But again, Dr. Shabir, I don't know why he's adding more stuff. That's making it more complicated. So 250 or 250 is 1. Sometimes they have like a shorter lens. So it's going to be a smaller D over here. And we're going to end up having like probably like a decimal or something, which ends up having, again, a smaller magnification or overall magnification, as I just said. The last thing is the depth of focus. Basically, it refers to the vertical distance from front to back. Added some noteworthy stuff to remember, and I'm pretty sure it's gonna be like, I can't even guess the questions that he's gonna put, and then the rest are basically like the types of microscope. I'm pretty sure you guys could just like see it on YouTube or something, you know. Good luck, and I'm sorry if I like said a lot of gibberish stuff or I confused you and didn't give you the full explanation, but I don't even understand the material fully myself. But yeah, good luck.